Unit 3 Chemical Kinetics, Chemistry Class 12. Speedrun. Objectives. After studying this unit, you will be able to define the average and instantaneous rate of reaction, express the rate of a reaction in terms of change in concentration of either of the reactants or products with time, distinguish between elementary and complex reactions, differentiate between the molecularity and order of a reaction, define rate constant, discuss the dependence of rate of reactions on concentration, temperature and catalyst, derive integrated rate equations for zero and first order reactions, determine the rate constants for zeroth and first order reactions, and describe the collision theory. Chemical kinetics helps us understand how chemical reactions occur. Chemistry, by its nature, is connected with change. Substances with well-defined properties are converted by chemical reactions into other substances with different properties. For any chemical reactions, chemists try to find out the feasibility of a reaction, which can be predicted by thermodynamics, as you know that a reaction with the change in Gibbs energy, which is less than 0 at constant temperature and pressure, is feasible. Extent to which a reaction will proceed can be determined from a chemical equilibrium. Extent to which, basically, the feasibility if the reaction will occur or not will be determined by the if the change in Gibbs energy is less than 0, then only it is the at constant temperature and pressure the reaction will be feasible. And second one, a chemist will try to find extent to which the reaction will proceed and can be determined from chemical equilibrium. Okay. Speed of the reaction, that is time taken by a reaction to reach equilibrium. Along with feasibility and extent, it is equally important to know the rate and factors controlling the rate of chemical reaction for its complete understanding. Along with feasibility and how much extent the reaction will happen, it is equally important to know the rate and the factors controlling the rate of chemical reaction for its complete understanding. How much fast the reaction will happen and the factors controlling this rate is important for us to know. For example, which parameters determine how rapidly food gets spoiled? How to design a rapidly setting material for dental filling? Or what controls the rate at which fuels burn in an auto engine? All these questions can be answered by a branch of chemistry which deals with the study of reaction rates and their mechanisms, called chemical kinetics. The word kinetics is derived from the Greek word kinesis, meaning movement. Thermodynamics tells only about the feasibility of a reaction, whereas chemical kinetics tells us about the rate of the reaction, so the speed of the reaction. For example, thermodynamic data indicate that diamond shall convert to graphite, but in reality the conversion rate is so slow that the change is not perceptible at all. Therefore, most people think the diamond is forever. Basically, according to thermodynamic data, we know that diamond will slowly get converted to graphite, but because the rate is so slow, the slowness is very, very slow. Because of such a reason, people think diamond will exist as a diamond forever. It's a misperception. Kinetic studies not only help us to determine the rate of chemical reaction, but also describe the conditions by which the reaction can be altered. They not only tell us how the speed of the reaction is, but it also tells us by which factors we can change or decrease the rate of the reaction. The factors such as concentration, temperature, pressure and catalyst affect the rate of the reaction. At macroscopic level, we are interested in amounts reacted or formed and the rates of their consumption or formation. At the large scale, we are not talking about molecules here, we are talking about amounts of substances, kg, grams. In such a case, in a macroscopic level, we are interested in only the amounts reacted or formed and the rates of their composition or for consumption, consumption or formation. Reaction is going on, we will care about if it how much it is getting consumed, how much the product is getting formed. And in the microscopic or the molecular level, the reaction mechanism involve orientation of energy molecules undergoing collisions. These are discussed. Macroscopic, we only know that reactant is getting consumed, product is forming, but that is only through macroscopic level. When we see in the molecular level, we see the arrangement of molecules, we see the collision of molecules, which is what the reason of the product formation is. The reaction mechanisms involving orientation, how the molecules are arranged or oriented, and energy, high energy, easy collision, more formation of product, more kinetic energy, more potential energy. All that we will discuss in case of molecular level. In this unit, we shall be dealing with average and instantaneous rate of reaction and factors affecting these. Some elementary, basically average means the total average, the average meaning the total reaction by total time, and instantaneous is the reaction happening at a specific instant or a specific amount of time or a specific instant of time, dt basically. Some elementary ideas about the collision theory of reaction rates are also given. Elementary ideas about the collision theory of reaction rates are also given. Okay, they said something about learning about the collision theory of the reaction. Fine. However, in order to understand all these, let us first learn about the reaction rate. First, we are going to read about the rate of a chemical reaction, starting off with the first topic in chemical kinetics. Some reactions, such as ionic reactions, occur very fast. For example, precipitation of silver chloride occurs instantaneously by mixing aqueous solution of silver nitrate and sodium chloride. Basically, the reaction is AgNO3 plus NaCl gives AgCl, which is a white precipitate, which will give a white PPT. This is an ionic reaction. This reaction is instantaneous, very fast. We saw that diamond converting to graphite is very slow. Exact opposite that, these ionic reactions are very fast, very instantaneous, in fraction of seconds. Happen in fraction of seconds. On the other hand, some reactions are very slow. For example, rusting of iron in the presence of air and moisture. Also, there are reactions like inversion of cane sugar and hydrolysis of starch, which proceed with a moderate speed. Like reactions very slow, as I said, diamond turning into graphite, or rusting of iron in the presence of air and moisture. This is also corrosion of iron. Basically, this is also very slow processes which take many months, years, so much time. And as for other reaction which can take few minutes, few hours, it depends. You must there are any other example for each category of 3 categories: very slow, moderate, and very fast. Very fast example is ionic reaction. Any kind of ionic reaction mostly will occur very fastly. And as for moderate reactions, metabolic reactions, we can say, or instantaneous reaction, very long reactions, rusting of iron, corrosion of various other metals, then that's some of the answers. You must be knowing that the speed of an automobile is expressed in terms of change in position or distance covered in a certain period of time. This is basically motion. This is kinematics, physics, chapters 2 to 4, I believe, 2 to 3. In that we saw that the speed is expressed by the distance covered by a certain period of time. Even in before classes also it is there. Similarly, the speed of a reaction or the rate of a reaction can be defined as a change in concentration of a reactant or a product in unit time. Rate equals to change in concentration by change in time. To be more specific, it can be expressed in terms of the rate of decrease in concentration of any one of the reactants, decrease in concentration in any one of the reactants, the rate of increase in concentration of any one of the products. Consider a hypothetical reaction assuming that the volume of system remains constant. Okay, the reaction is reactants turning into products R to P. 1 mole of reactant R produces 1 mole of the product P. If R1 and P1 are the concentration of R and P respectively at time t, and R2 and P2 are the concentration at time t2, then delta T is T2 minus T1, delta R is R2 minus R1, delta P is P2 minus P1. The square brackets above the equation are used to express molar concentration. Rate of disappearance of R, decrease in concentration of R, we take minus because it is decrease in concentration of R, delta R by delta T. Then rate of appearance of P, increase in concentration of P by time taken. Here we take it as plus because it is appearing, it's a product. Since delta R is a negative quantity, delta R is a negative quantity, as concentration of reactant is decreasing, it is multiplied with minus 1 to make the rate of reaction a positive quantity. Basically, here it is minus because of one more reason. Basically, when we take R final minus R initial reactant, we know that when the reaction is going forward reaction, then R initial would be greater than R final. R initial would be greater than R final. So this will get a negative value. To avoid a negative value in this equation for the rate, we take a minus sign here. Minus times minus, we will get a positive rate. That is what they said. Equation 3.1 and 3.2 given represent the average rate of a reaction R average. Equations 3.1 and 3.2, these are the average rate of the reaction. Basically change, disappearance in reactant and appearance in product. Average rate depends upon the change in concentration of reactants or products and time taken for that change to occur. Instantaneous and average rate of a reaction. Let's see. This I believe is the instantaneous one. Yes, I think so. This is the time. The time is in the x-axis. Concentration of reactants is in the y-axis. Okay. As the reaction goes forward, the concentration of reactants should reduce. That is what is happening here. As we go forward, the rate of the reaction is reducing. That is as it should be. Then this is at times t1 and at times t1 the concentration is around R1, whereas at time t2 the concentration is around R2. This is what we call delta R, the change in concentration. Basically they are doing a graph here. This is the R average. This graph here is R average and they are taking a tangent here. Minus delta R by delta T, which is equal to minus of R2 minus R1, T2 minus T1. And in case of instantaneous, it is minus dr by dt because d is taken for a small quantity, and here the slope is negative. Okay, just seems confusing, but it is the same thing. It is just they're calculating average speed, average rate, which is average is they substituted in this formula, and in case of instantaneous they substituted in this formula, and the slope is the division of the y coordinate, change in y coordinate by x coordinate. So in such a case where the value is negative, the slope is also negative. And in case of the concentration of products, as the forward reaction, if for a forward reaction as time increases, the concentration of product also increases. At time t1 product concentration is p1, and at time t2 product concentration is p2. In such a case the rate average is delta p by delta t, which is p2 minus p1 by t2 minus t1. Okay, And in case of R instantaneous, we take dp by dt, which is equal to the slope. Okay, fine. Same thing again repeated here. Units of a rate reaction. Units of rate of a reaction from equations 3.1 and 3.2. Okay, the equations are basically this equation: delta minus delta R by delta T and delta P by delta T. Okay, it is clear that units of rate are concentration per time. Basically, when we saw that rate equals delta concentration change by delta time. Concentration is concentration term. Then if we want to find the unit of R rate, it will be concentration per time. Concentration we can write it as, in case of molarity, it is mole per liter whole per time. This can be written as mole per liter whole per second. This is basically the unit for the rate of a reaction. Okay, fine. For example, if the concentration is in mole per liter and time is in seconds, then a unit will be mole per liter per second. However, in gaseous reaction, when concentration of gases are expressed in terms of their partial pressures, the unit of rate equation will be atm per second. Basically, in liquid solutions, we take it as delta C by delta T. But when it is gaseous equations, we do not take concentration, but we take change in their partial pressures. Partial pressure is the pressure of the individual gas in the total vapor pressure, or the total pressure, delta P by delta T, where P is the partial pressure. Okay, fine. And here we know partial pressure, we can take the pressure unit as Pascal, atm, bar, torr, whatever we want, we can take it, or mm per hg, whatever it might be. It will be pressure per time. This will be the unit then. Let's see the example here. From the concentration of butyl chloride at different times given below, calculate the average rate of the reactions. Average rate of the reaction. Butyl chloride plus H2O. The reaction is forming C4H9OH. Basically, butyl chloride is forming butanol. Butanol and HCl. This is a displacement reaction where, okay, fine. During time intervals Ts, where at 0 it is 0.1 mole, at 50 seconds it is 0.0905, which is around 0.095 degrees. Okay, we can see in the solution, we can determine the difference in concentration over different intervals and time, and thus determine the average rate by dividing delta T by delta T. Okay, all have Basically individually we should find. Here at the start of the reaction at time 0, the butyl chloride is 0.1 mole, whereas the butanol is 0. So as this increases, as the reactant decreases, product will increase, and individually we should find out for all the times. Here, from seeing this table, that average falls from 1.90 into 10 power minus 4. It is 10 here. To 0.4 into 10 power minus 4 mole per liter per second. Okay, however, average rate cannot be used to predict the rate of reaction at a particular instance, as it would be constant for the time interval for which it is calculated. So, to express the rate at a particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate of the smallest time interval dt. When delta t approaches 0, the change is almost 0. Hence, mathematically, for an infinitesimally small dt, instantaneous rate is given by, this is for reactant, this is for product. When t is reaching 0, it will be minus dr by dt and dp by dt. Instantaneous rate of hydrolysis of butyl chloride. As the time increases, the concentration of butyl chloride decreases, and for example, instantaneous rate at t equals 600 second. This is the rate. At there we should take a tangent and we should find a small distance, and we can find the total rate at that instant. It can be determined drawing graphically a tangent at time on either of curves for concentration r and t versus time, and calculating its slope. So in problem 3.1, r instantaneous at 600, for example, can be calculated by plotting a concentration of butyl chloride as a function of time. A tangent is drawn that touches the curve at t equals 600 second. The slope of tangent gives the instantaneous rate. At 600, they basically substituted the values here, the change in concentration at the time, 800 minus 400, initial and the final, and we will get it to be around 5.12 into 10 power minus 5, 0.5 basically, 0.5 into 10 power minus 4 mole per liter per second. At time equals 250 seconds, the same way they calculated r instantaneous at time equals 250 seconds, which is around 1.22 into 10 power minus 4 mole per liter per second. At 350 seconds, r instantaneous 1 into 10 power minus 4 mole per liter per second. At t equals 450 seconds, r instantaneous is 6.4 into 10 power minus 5 mole per liter per second. Over these are just the values, so it's not another x. Now consider a reaction, mercury reacting with chlorine to give mercury chloride, where stoichiometric coefficients of the reactions and products are same. Thus the rate of the reaction is given by, when stoichiometric coefficients are same, all are 1. Then rate of reaction is disappearance of Hg by time, disappearance of chlorine by time, appearance of Hg chloride by time. That is, rate of disappearance of any substance of the reaction is same as the rate of appearance of the products. But in the following reaction, 2 moles of Hi decompose to produce 1 mole of each H2 and I2. Basically, hydrogen iodide is decomposing to hydrogen gas and iodine. For expressing the rate of such a reaction where stoichiometric coefficients of reactants or products are not equal to 1, rate of disappearance of any one of the reaction and rate of appearance of product is divided by the respective stoichiometric ratio. coefficients. Basically they are saying we will divide them by the respective stoichiometric coefficients, where we see here rate of reaction for HI, this is the disappearance of HI, is minus 1 by 2. 1 by 2 we took it is because here the stoichiometric for HI is 2 and we divided it by 2. So it will be 1 minus 1 by 2 delta HI times by delta T, which is equal to delta H2 by delta T, and which is equal to delta I2 by delta T. And here there is no stoichiometric, actually there is 1 here, so when we divide it with 1 there is no change, so it is not expressed. Since rate of consumption of HI is twice the rate of formation of H2 or I2, to make them equal, the term delta HI is divided by 2. The rate of the reaction is given by this reaction. Basically, because the HI is like getting reduced, I mean getting decomposed to give 2 of its own, so we need 2 of them, and dividing it by 2 will give us a whole rate of reaction. But when we want the individual rate of disappearance of HI, then we will not divide it by 2. We will not divide it by 2 when we want the rate of disappearance of HI. We will not use stoichiometric coefficients when there is rate of disappearance or rate of appearance. And similarly, one more reaction example. For the reaction, 5 bromide ions plus bromo oxide plus 6H plus gives 3Br2 and plus 3CH2O. Here, bromide ions disappearance minus 1 by 5, which is equals to BrO3 minus has no coefficient, or it has a coefficient of 1, so there is no change, and this rate of reaction for BrO3 will be equal to the rate of disappearance of BrO3 minus, and this is equal to 6H plus are getting disappeared, so minus 1 by delta H plus by delta T, which is equal to, in the product side there are 3 bromine is formed, 3 bromine Br2 is formed, so 1 by 3 delta Br2 by delta T and 1 by 3 H2O by delta T. This is also because there is a stoichiometric coefficient for H2O. For gaseous reaction at a constant temperature, concentration is directly proportional to the partial pressure of species, and hence the rate can be expressed as a rate of change of partial pressure of reactant or the product. Basically they are saying for a gaseous reactant, when the reactant is a gas, that is at a condition of constant temperature, the concentration of the gaseous reaction, gaseous reactant is directly proportional to the partial pressure of the species. Higher the partial pressure, higher the concentration, and same reaction we can write in terms of partial pressure as well. That is what they said in that statement. Example, the decomposition of dinitro oxygen pentaoxide, dinitrogen pentaoxide in chloroform, not chloroform, it is carbon tetrachloride at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 mole per liter, and after 184 minutes is reduced to 2.08 mole per liter. The reaction takes place according to the equation. 2N2O5 gives 4NO2 nitrogen dioxide and oxygen, 1 mole of oxygen. Calculate the average rate of this reaction in terms of hours, minutes and seconds. What is the rate of production of NO2 during this period? Average rate, we take the whole rate of the reaction. ROR, or rate of the reaction, is the same as the average rate of the reaction, but appearance or disappearance, we do not take the coefficients. For the average rate or the rate of the reaction, we take the coefficients, we divide it by the coefficients. Here we see for disappearance of dinitrogen pentaoxide, we divide it by 1 by 2, and this is a disappearance, so it is minus delta concentration change of N2O5 by delta time. And here we will get in case of minutes, we will get it to be around 6.79 into 10 power minus 4 mole per liter per minute. This is in case of minute. But in case of hours, if we want, we multiply it by 60. We divide it by 60. In case of hours, if we want, we divide it by 60. Minute is 1 by 60th of no, we multiply it by 60 actually, yeah. We multiply it by 60, then we will get 4.07 into 10 power minus 2 mole per liter per hour. But in case if you wanted in seconds, then the same from minute we will divide it by 60, or from hour we will divide it by 3600. We will get the final answer in seconds to be 1.13 into 10 power 5 minus 5 mole per liter per second. It may be remembered that rate equals 1 by 4 delta NO2 by delta T, which is around equal to be, wait, this is the total ROR, average rate or rate of reaction. Rate of reaction, this is not an ether, this is a rate of reaction. Rate of reaction, this is the rate of reaction, but in case of this one, this is not the rate of reaction. This is the disappearance, wait, no, this is the appearance of NO2. In case of appearance of NO2, we shift the 1 by 4 to this side. That is why there is a 4 here. Then we multiply the rate of reaction with this 4. We will get the rate of appearance of nitrogen dioxide is 2.72 into 10 power minus 3 mole per liter per minute. Okay, let's see the in-text questions. For the reaction R to P, where R is the reactant and P is the product, the concentration of reactant changes from 0.03 molar to 0.02 molar in 25 minutes. Calculate the average rate of the reaction using units of time, both in minutes and seconds. Basically the same as the previous solution example we saw. They gave the change, they did not give the change directly, but they gave the initial and final concentration. Then with subtraction we can find the change in the concentrations. Then change in concentration by time is what we call as the rate of the reaction. In such a case we will get the rate of reaction in 25 minutes, I mean in minutes, mole per liter per minute. If we want to get it, if you want to convert it to seconds, then we will divide the equation which we get in terms of minutes by dividing it by 60. And if we want to convert the minutes solution into hours, then we multiply the equation times 60. That is the answer. That is how to do the first question. In reaction 2A gives products, the concentration of A decreases from 0.5 molar to 0.4 molar in 10 minutes. Calculate the rate during this interval. They are asking the rate of the reaction, so we need to take this stoichiometric coefficient into consideration. So basically delta A by delta T by 2, which is the whole thing is divided by 2, and in such a case we will get the total rate of the reaction. If they give the initial and final concentration, we subtract it, we will get the change in reaction. Now the next main topic is factors influencing the rate of a reaction. Factors influencing rate of a reaction. Rate of a reaction depends upon the experimental conditions such as concentration of reactants. Basically they are saying rate of reaction depends on the concentration of reactants, pressure in case of gases, temperature of the system, catalyst, presence of a catalyst. Catalyst is basically it does participate in the reaction, but it is not present in the products or chemical in the reactant side. It just increases the rate of the reaction. It controls we can say catalyst is something that controls the rate of a reaction. It can either increase the reaction, I'm not sure if it can decrease the reaction, but basically catalyst is used in case of increasing or amplifying the rate of the reaction. And under the factors influencing rate of reaction, the first topic is 3.2.1, dependence of rate of the reaction on the concentration of reactants. The rate of chemical reaction at a given temperature may depend on the concentration of one or more reactants and the products. The representation of rate of reaction in terms of concentration of the reactants is known as the rate law, integrated rate law. It is also called as a rate equation or rate expression. Basically, when we are expressing the rate of reaction in terms of the concentration of the reactants or product of the concentration of the reactants, that is known as rate law. Basically they are saying rate is directly proportional to the concentrations of reactants. For a reaction A plus B gives C plus D. A plus B are the reactants. So the concentration of where rate is depending on the product of the concentration of the reactants whole power xy or anything it might be, and basically defining a rate via the concentration, the product of the concentration of the reactants is known as the rate law or rate equation or rate expression or integrated rate law. Rate expression and rate constant. The result table 2.1, 3.1, that table or the question, basically they showed number of values change in concentration per at some time change. The rate of reaction decreases with the passage of time as concentration of reactants decrease. Let's inspect the table once more. Here we see that this is the rate of the reaction. Basically this is the rate of the reaction in terms of 10 power minus 4. This is minus 4. In terms of 10 power minus 4, the rate of the reaction is around 1.90. That is at when the time is 0 to 50 seconds. It is the highest, and as we seem to go down due to some factors, which is the decrease in the concentration of the, as we go from the 0 seconds to 50 seconds or 50 seconds to 200 seconds, the concentration of reactant is decreasing. For a forward reaction, the concentration of reactant decreases and concentration of product increases. In such a case, when the concentration of product is decreasing, the rate of the reaction is also decreasing, and it might depend on not only the rate, the concentration of the reactant, it may depend on other factors such as temperature and pressure also for gases. As in case of if it is a gaseous reaction, as the reaction goes forward, the partial pressure of the reactant keeps on decreasing. That will also affect the rate of the reaction. In this case, as the concentration of reactant is decreasing, clearly we can see here where it is going from 0.1 to 0.9 to 0.8 to 0.7 to 0.6 and 0.4 and 0.2. As we go down, the concentration is decreasing, and the highest value is 1.90, close to 2, and the lowest value is 0.4. It keeps on decreasing as we see concentration is decreasing. That is what they are saying here. Clearly show that rate of a reaction decreases with the passage of time as the concentration of reactants decrease. Conversely, rates generally increase when reactant concentration increases. As reaction concentration increases, the rate also generally, in a general case, as the higher the concentration of reactant, higher the rate of the reaction, forward rate of the reaction. Just a minute. Okay, now let's see. Basically they're saying that as the concentration of the reactant goes on decreasing, the rate of the reaction also decreases. And inversely, we can say that as the concentration of the reactant increases, the rate of the reaction also increases. When reactant concentration increases, the rate will also generally increase. So the rate of the reaction depends upon the concentration of the reactants. Basically this one. Consider a general reaction. AA plus BB gives CC and DT. Basically, small a, b, c and d are the stoichiometric coefficients of the reactants and products, and a, b and cc capitals or caps are basically the elements or molecules which are reacting. A, b, c and d, the small ones, are the stoichiometric coefficients of reactants and products. The rate reaction or expression for this reaction is rate is directly proportional to a power x power times b power y, what I wrote here. Basically it depends on the concentration of the reactants, where x and y are the exponents and may or may not be equal to the stoichiometric coefficients a and b of the reactants. Above equation can also be written as, we are basically introducing a proportionality constant here, where rate equals k a power x times b power y, and we know that the rate of the reaction in case of reactant is minus dr by dt. Here r is not the rate of the reaction but the concentration of the reactant. In such a case, minus dr by dt equals k a power x times b power y. Okay, fine. This form of equation 3.4 is known as differential rate of the equations. Okay, this form basically 3.4b equation is known as the differential rate equation, where k is the proportionality constant called the rate constant. The equation 3.4, which releases the rate of reaction, which relates the rate of reaction to concentration of reactant, is called the rate law or rate expression. Thus, the rate law, basically the definition for rate law, brace yourself, the rate law is the expression in which reaction rate is given in terms of molar concentration of reactants, with each term raised to some power which may or may not be the same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. Okay, fine. Let's read it again. Rate law is the expression of in which reaction rate is given. Okay, reaction rate. This reaction rate we are giving in terms of molar concentration. Okay, rate we are giving in terms of molar concentration, that is of the molar concentration of the reactants, and this each term of the molar concentration of the reactants is raised to some power, and this power may or may not be equal to the stoichiometric coefficient of the reacting species in a balanced chemical equation. Okay, basically they are saying that rate law is something like where we are relating a rate to the individual concentration of the reactants, which are raised to some exponential powers, and these powers don't need to be equal to the coefficients, stoichiometric coefficients. Basically there is no relation between them. They might be equal, they might not be equal, and this is how we find x and y here in this equation. Is we do not find them out, they are experimentally found out. For example, 2NO, and we can only find them when sufficient information is given. Normally this equation is experimentally found out, and the values of a power x and b power y are experimentally found out, but in case where sufficient information is given, we can indeed find the x and y. Basically in this case we can define one more thing here, order of the reaction, where order of the reaction is the sum of the exponential powers of the reactants concentrations. X plus y is the rate of the reaction, I mean not rate, the order of the reaction. And this equation is a differential form of the equation, differential rate equation, and they give an example here. NO2 plus NO, nitrogen monoxide, plus oxygen gives 2 nitrogen dioxide. Okay, we can measure the rate of this reaction and as a function of initial concentration, either by keeping the concentration of one of the reactants constant and changing the concentration of other reactant, or by changing the concentration of both the reactants. Okay, fine. You can measure the rate of this reaction as a function of initial concentration. You can measure the rate of this reaction as a function of initial concentrations. As a function of initial concentrations. Okay, by keeping the concentration of one of the reactants constant. Keeping the concentration of one of the reactants constant, and changing the concentration of the other reactants, or by changing the concentration of both the reactants. Can keep the concentration of one of the reactants constant, the concentration of one of the reactants constant, and changing concentration of the other. Okay, keeping the concentration. Okay, fine. Let's see more. The following, by doing that tweaking in the concentrations, we will get results of when the initial concentration of nitrogen monoxide is 0.3 molar and the initial is 0.3 molar for oxygen as well, then the initial rate is 0.096, and we will keep the rate of oxygen common, like a constant. Change NO, then the rate of reaction is increased by 0.384. It is increased because the concentration of the nitrogen reactant is increased. Okay, let's see the third case scenario. We take initial as 0.30 and the nitrogen monoxide, we take it as 0.30, but this time we will increase the concentration of oxygen, which we will convert it into 0.60. Let's see when we increase the oxygen concentration. Here we see that the increase in rate is a little less compared to the second case where we increase the concentration of NO, which is 0.384. But here, even though increased by the same amount, the molar in concentration terms, the rate of the reaction increased more when we increase the rate of increase the concentration of the nitrogen monoxide compared to when we increase the concentration of the oxygen. Let's see what will happen when we increase the rate of both the concentration of both the reactants. When we increase both to 0.6, then the rate is almost 8 times the initial, where it was 0.3 moles basically. So here we see, here we can understand based on the second and third cases that it depends, the rate of the reaction depends more on the amount of NO present. So higher the NO, the higher the rate of the reaction. So it might, when we can say that nitrogen monoxide is controlling the rate of the reaction or increasing the rate of reaction more than oxygen. It is obvious looking after at the results that when the concentration of nitrogen monoxide is doubled and that of oxygen is kept constant, then the initial rate increases by a factor of 4 from 0.96 to 0.384. This indicates that the rate depends upon the square of the concentration of nitrogen monoxide. Okay. Basically, when we take 2a power A is nitrogen monoxide, let's take it as nitrogen monoxide as well, 2NO whole square, then we will get it as concentration of NO times 4, and in case of the initial one, rate equals NO. So when we see that the rate uh, got 4 times of the initial reaction, we can conclude that the rate, it depends on the square of the nitrogen monoxide. When concentration of nitrogen monoxide is kept constant and the concentration of O2 is doubled, the rate is also get doubled, indicating that the rate depends on the concentration of O2 to the first power. In case of oxygen, the same scenario, it became 2O2 equals 2 times of O2 itself. There is no squares or powers here. The rate doubled, so we will get that 2O2 itself. So power is 1 here. Here the power is 2, but here the power is only 1. This we can indicate based on the experimented here. Hence, the rate equation for the differential form for this rate expression is given as minus dr by dt equals KNO2 times O2. Basically, here what we deduced that the rate of the reaction increased by 4 times, by a factor of 4, when we doubled the concentration of nitrogen monoxide. But it doubled, the rate of the reaction only doubled or increased by a factor of 2 when we doubled the concentration of the oxygen. Because of such a reason, we concluded that the concentration of the first nitrogen monoxide has a power exponent of 2 and oxygen has an exponent of 1. K is the normal rate constant and is the differential form minus dr by dt, the change in reactant concentration. Now we observe that for this reaction in the rate equation derived from the experimental data, the exponents of the concentration terms are the same as their stoichiometric coefficients in the balanced chemical equation. In this case, we see the reaction is nitrogen monoxide, 2 moles of nitrogen monoxide plus 1 mole of oxygen gives 2 moles of nitrogen dioxide. In such a case, the stoichiometric coefficient of nitrogen monoxide is 2. Nitrogen monoxide is 2. Here the power as well is 2. It doesn't mean they're repeating going on and on again, that it may be like that. It is not compulsory that every time the rate reaction has to be the power or the exponent should be same as the coefficient. It can be sometimes, that is all. Where oxygen as well, if we see the moles of oxygen is 1, the power is also 1. But it doesn't mean it can be like that every time. Now we observe that for this reaction, the rate equation derived from the experimental data, the exponents of the concentration terms are same as their stoichiometric coefficients in the balanced chemical reaction. Some other examples are given below. Reaction chloroform plus chlorine gives carbon tetrachloride plus HCl. Here the rate is CHCl3 1 and chlorine 1 by 2. Here the stoichiometric coefficient of chlorine is 1, but we took the power as 1 by 2. That is exactly what the NCERT said. It doesn't need to be the same. In case of second reaction, where it is CH3COC2H5 plus H2O, it is basically methoxyethanoate plus H2O reacting with water will give us ethanoic acid plus ethanol. The rate of this reaction, it doesn't depend on the concentration of water. When we get the concentration of water power 0, we can say that it doesn't depend on the concentration of water. Whatever the concentration of water might be, it only depends on the concentration of the methoxyethanoate. The rate depends only on the concentration of the methoxyethanoate. That is why only methoxyethanoate has a power of 1 and water doesn't have a power. It has power of 0. In these reactions, the exponents of the concentration terms are not the same as their stoichiometric coefficients. Thus, we can say that the rate law for any reaction cannot be predicted by merely looking at the balanced chemical equation, that is theoretically must be determined experimentally. It is a statement can be asked as a statement question. Next topic is the order of a reaction. In the rate equation 3.4, rate equals Ka power x times B power y. X and y indicate how sensitive the rate is to the change in concentration. As how sensitive meaning how much the concentration affects the rate of the reaction. If the x and y value is really high, we can say that for a slight change in concentration, the rate of the reaction will have an exponential change, or we can say a very large change or an enormous change. That is to us when the number of the value of x and y is very high. We can say that for every slight change in concentration, the rate of the reaction will change exponentially, or enormously. But when the x and y values are very less or very small or even can be zero, that means the change in concentration doesn't really affect the rate of the reaction. The rate of the reaction when x and y values are very small doesn't depend on the rate of the reaction. Rate of the amount of the concentration. That is what they mean by how sensitive the rate is to the change in concentration of A and B. Sum of these exponent, that is x plus y, gives the overall order of the reaction, whereas x and y represent the order of the reaction with respect to reactants A and B respectively. X plus y is the total order of the reaction, and x and y separately, individually, x for the order of the reaction with respect to A and y with order of the reaction with respect to B. Hence, the sum of powers of the concentration of the reactants in the rate law expression is called the order of the chemical reaction. Basically, they are saying the sum of the exponents or the sum of the powers of the concentration of the reactants in an experimentally proven reaction, proven rate or rate expression from a experimentally proven rate law expression, then we can say x plus y equals the total order of the reaction. The order of the reaction can be 0, 1, 2, 3 and even a fraction. In this case we saw an example here. In this case where we saw the chloroform reacting with chlorine to give carbon tetrachloride and HCl, the rate of the reaction in case here, when we add up the powers, it is 1 plus 1 by 2. The order of the reaction is 3 by 2. It's a fraction. And in case of here, the order of the power of H2O is 0, which means it doesn't depend on the concentration of H2O. Or we can say H2O can be taken in excess here. It doesn't depend on the concentration of H2O. It only depends on the concentration of the methoxyethanoate. And here the order of the reaction is 1 plus 0, which is 1. We can call this the second reaction, methoxyethanoate reacting with water. We can call it as the first order reaction. And based on the orders, we can call reactions as 0th, first, second and third order reactions, or even more. A zero order reaction means that the rate of the reaction is independent of the concentration of the reactants. If it is a 0th order reaction, then we can say that no matter how we change the concentration, the rate will remain constant. The rate will not change. When we take, actually it's better I think to go to what. Okay. This is chemical kinetics, unit 3. Basically, we know that rate depends on the concentration of A and B, powers x and y. Rate equals, this is a rate law. and we know that x plus 5 from above equation is the order of the reaction. In case of 0th order reaction, in case of a 0th order reaction, where R equals K times A power 0 plus B power 0. They cannot be negative, so both should be 0. In such a case, where anything power 0 is 1, so we can say R is directly equal to K. So since K is the rate constant, the rate will always be constant in case of a 0th order reaction. And of course, this is only with regard to concentration. If there is a change in concentration, the rate will always be constant. The rate will not change with even a slight or a large change in the concentration. Okay. That is what they mean by being independent of the concentration of the reactant. Calculate the overall order of a reaction which has a rate expression 1 by 2, 3 by 2. It is basically 4 by 2, which is the second order reaction, and in case of 3 by 2 minus 1, wait, it can be minus 1 it seems. So in case of minus 1, it can be negative, sorry. And in case of this second, it is a 0.5 order reaction. In case of A, it is x plus x by y, so it is a second order reaction. And in case of B, the solution is half order reaction. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. Actually, what happens more specifically in a half order reaction? In a half order reaction, R equals K A 1 by 2, let's assume. Then let's assume the concentration is 4 in the initial, like first case scenario. Then rate is for root 4, so it is 2 times of K. This is the first case scenario. It is in this half order reaction also, it is greater than the rate constant. Rate is actually greater than the rate constant. Let's take for a second case, it is 9. The concentration increased, where K times 9 whole root R equals 3 times of K. Where here as well we see that the rate increased as well. Here as well we can say rate is directly proportional to the reactant concentration. This square bracket represents the concentration. In both the cases, it is directly proportional to the concentration of the reactant. Fine. Okay, let's continue. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. In some of the reactions which we saw, which are involving many number of molecules, many kind of steps, these are what we call a complicated or complex reactions, and we never get the idea or true picture. In such a reaction, we never get idea of how the reaction is actually taking place, like which is colliding with which first, what reaction is happening first. We do not get the idea, and for such reactions we do not get the idea. So we want the idea of what is going on. So for such a reason, we need one step reaction. The reactions taking place that is one step are called elementary reactions. Elementary reactions are one step reactions. When a sequence of elementary reactions called mechanism gives us the products. The reactions are called complex reactions. Single step elementary reaction. Many steps involved complex reaction. These may be consecutive reactions. Example, oxidation of ethane to carbon dioxide and H2O passes through a series of intermediate steps which alcohol, aldehyde and acid are found. Basically, oxidation of ethane to carbon dioxide, this is actually a complex process where many intermediate steps in which alcohol, aldehyde and acid groups are formed. Reverse reactions and side reactions. Example, nitration and phenol yields orthonitrophenol and paranitrophenol. They gave one more example here. Reverse reaction and side reaction. Example, nitration of phenol yields orthonitro and paranitrophenol. Okay, these are the major and minor products. Fine. Units of a rate constant. For example, for general reaction, this reaction rate equals K A to the power of X times B to the power of Y, where X plus Y is the order of the reaction, where it is represented as N. K equals rate by product of concentration, where concentration rate is concentration by time and times 1 by concentration because this is the Ax power Y. And in this case, the concentration power, if we see, it is not a unit concentration. It is not a single concentration or mole per liter, we cannot say this. It has a specific power. And that power is the order. So we will see that the rate constant varies with respect to the order of the reaction. Taking SI units of concentration, mole per liter and time seconds, the unit of K for different reaction orders are listed in the rate constant. In a zero order reaction, we see order is 0, so mole per liter whole power 0, it will be same as the normal, so this is into 1, so it will be mole per liter per second itself. For zeroth order reaction, the rate is equal to the rate constant, both magnitude wise and unit wise. And in case of first order reaction, mole per liter per second by mole per liter get cancelled. We are reminded with per second. In case of a second order reaction, these are the units of the rate constant. In case of a second order reaction, mole per liter per second times mole per liter whole square. N is 2, so we square it. And mole per liter per second mole, basically it is liter per mole per second, where liter has a positive power. Anyways, identify the example is identify the reaction order from each of the following rate constant. Basically they gave a specific rate constant. Here if we see, it is L minus 1, S minus 1. So we know that we got this from this equation, where it is 1 by concentration by N. So we can write it as concentration, since we can write concentration as concentration times concentration N minus N, and because the bases are same, concentration of 1 minus N. In such a case, the concentration is mole per liter. Then if we introduce 1 minus N, it will be mole 1 minus N, and liter it is N minus 1. This will be the concentration, and second inverse will be, not second inverse, when we write it down, it will be the same. In such a case, Here if we see, we will get it as a first order reaction. I mean, no, it's a second order reaction for this one. Second order, first order. That is second order as I said before, and first order for the second one. Now another topic, molecularity of a reaction. Another property of a reaction called molecularity helps in understanding its mechanism. The number of reacting species, atoms, which can be atoms, ions or molecules, taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is okay. Okay, let's read that again. Another property of a reaction called molecularity helps in understanding its mechanism. The number of reacting species, atoms, ions, or molecules taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called molecularity of a reaction. Basically, the number of reacting species, which can be atoms, ions, or molecules, that is taking part in an elementary reaction, a single step reaction, which must collide simultaneously in order to bring about a chemical reaction is called molecularity of a reaction. Okay, basically the number of molecules or atoms or ions or reactant species participating in an elementary reaction to bring about the reaction is what we call molecularity of the reaction. The reaction can be unimolecular when one reacting species is involved, for example, decomposition reactions like decomposition of ammonium nitrate, NH4NO2, N2 plus H2O, and biomolecular reaction involves simultaneous collision between two species. For example, dissociation of hydrogen iodide, HiH2 plus I2. This is also dissociation of hydrogen iodide, where this is a biomolecular reaction, not because it's a it is because it's a biomolecular reaction because two molecules of HI, 2 moles of HI, no, it is 2 molecules of HI dissociate to give H2 plus I2. Trimolecular reactions or termolecular reactions involve simultaneous collision between 3 reacting species. For example, 2 NO and 1 oxygen molecule. This is not a tetramolecular reaction because O2 is a single molecule and there are 2 molecules of NO, nitrogen monoxide. In this case, a 3 molecules will collide to bring about the forward reaction, which is nitrogen dioxide. The probability that more than 3 molecules can collide and react simultaneously is very small. Hence, reactions with molecularity 3 are very rare and slow to proceed. 4 3 is the highest. 4, it is very rare for 4 individual molecules or atoms or ions to collide simultaneously. It is very hard and very slow process as well. It is very rare, and in case of this 3 molecularity also, it is also very rare and slow to proceed. This is also slow reaction. So therefore we can say the maximum is around 3 itself. 3 is the maximum molecularity. It cannot be 0 molecularity. It should be 1, 2 or 3. It is therefore evident that complex reaction involving more than 3 molecules in the stoichiometric equation must be taking place in more than one step. With this molecularity being maximum being 3, when we see equations, we can determine it is a elementary reaction or a complex reaction by seeing if the molecularity exceeds 3, then it is said to be a complex reaction. It is not undergoing in a single step. In case of potassium chlorate reacting with ferrous sulfate plus sulfuric acid gives KCl, ferrous sulfate, ferric sulfate and H2O. This reaction, which apparently seems to be of a 10th order, is actually a 2nd order reaction. This is not a 10th order reaction. This shows that this reaction takes place in several steps. Which step controls the rate of the overall reaction? Like we say, the reaction is a total of many steps. So how can we say the total order of the reaction is 2? We are dividing the equation or reaction into many steps. Many steps we are doing that. Then how can we say which is the total order of the reaction? We say the total order of the reaction is the order of the slowest step of the reaction. The question can be answered if we go through the mechanism of the reaction. For example, chances to win the relay race competition by a team depends upon the slowest person in a team. A relay race is basically a race competition, and in such a case, it doesn't depend on the fastest player, but it depends on the slowest player. The slowest player, if he runs, basically if all the players are fast, also if the slowest player is very slow that he cannot complete the race, others will surpass him even if the other players of the team are fast. And basically it means that the race depends on the slowest person. In the same way, the reaction here also depends on the slowest step. Similarly, the overall rate of the reaction is controlled by the slowest step in a reaction called the rate determining step, RDS. Consider the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in an alkaline medium. Consider the decomposition of hydrogen peroxide, H2O2, which is catalyzed by iodide ion in an alkaline medium. Okay, fine. Is getting decomposed into 2H2O, gives 2H2O plus O2. The rate of this reaction is found to be 2. The rate of reaction is Wait. The rate of the reaction is based on this should be 2, but this reaction is first order with respect to both H2O. Okay, this is with respect to individual reactants, it is first order. Evidences suggest that this reaction takes place in 2 steps. Basically, but even though this is individually H2O2, it's first order, but normally the whole reaction should be second order. But based on certain evidences, this is not a single step elementary reaction. This is H2O2 plus iodide, which gives H2O plus iodine oxide, and H2O2 reacting with iodine oxide to again give H2O plus I minus iodide ion plus oxygen. This is a 2-step reaction. In this case, both the steps are bimolecular elementary reaction. Species IO is called an intermediate since it is formed during the course of the reaction but not in the overall balanced reaction. The first step, being slow, is the rate determining step. The first step for hydrogen peroxide reacting with iodide ion to give H2O water plus iodo oxide, basically IO minus, is a slow step, and this is also the first step is also the rate determining step because it's the slowest step. Thus, the rate of formation of intermediate will determine the rate of this reaction. Intermediate is IO minus. Thus, from the discussion till now, we can conclude the following. First, we conclude that order of a reaction is an experimental quantity. It can be 0 and even a fraction, but molecularity cannot be 0 or a non-integer. Basically, it means that order of a reaction is experimentally found out and it can be 0, 1, fractions, etc. But molecularity cannot be 0 or a fraction. This is because when it is a 0, molecularity is 0, there is no molecule, there is no collision, there is no molecules, there is no reaction. So it cannot be 0. It can only be a 1, 2 or 3. 3 is the maximum. Above 3, the reactions are very rare. And second, we conclude order is applicable to elementary as well as complex reactions, whereas molecularity is applicable only for the elementary reaction. Order, we saw it is applicable in the first reaction. We saw here directly from H2O2 to H2O and O2. With respect to H2O2 and iodine ion, we can say that the reaction is first order. But in case of the elementary reaction also we can determine the order. And it can be applicable to both elementary reaction, single step reaction as well as complex step reaction. We are basically saying the whole reaction is a second order reaction in case of the potassium chlorate reaction here, this one. We are saying it's a second order reaction, which means the order is applicable to the whole reaction, whole complex reaction as well. But molecularity cannot be applied for complex reactions because molecularity cannot exceed 3. In such a reaction, it only works for elementary reaction, a single step reaction. For example, for complex reaction, molecularity has no meaning. Third conclusion, for complex reaction, order is given by the slowest step and molecularity of the slowest step is the same as the order of the overall reaction. Order for a complex reaction, order is given by the slowest step and molecularity of the slowest step is the same as the order of the overall reaction. Okay, fine, that is also, I understood that. Basically, it means that the order of the whole reaction depends on the slowest step and the order of the slowest step is the same as the order of the overall reaction. Now let's see the in-text question. For reaction A plus B giving the product, the rate law is given by R equals K times A power 1 by 2 and B power 2. What is the order of the reaction? It is 1 by 2 plus 2. It is either 5 by 2 or 2.5. The conversion of molecules X to Y follows the second order kinetics. The conversion of molecules X to Y follows the second order kinetics. Wait. Okay, X is the reactant. Basically, the reaction is from X to Y. X is the reactant, Y is the product. And this is a second order reaction. They are saying if concentration of X increases 3 times, it is a second order reaction, N equals 2. And if the concentration of X concentration is increased to 3 times, how will it affect the rate of the formation of Y? 2 power 3, it is 8 times. The rate of the reaction basically will be increased. I think so. Basically they are saying X to Y, N equals 2, rate equals K times X power 2. They are asking if X is 3 times X, then K equals 3 times whole power square, then it is equal to 9 times K X power 2. So the rate of the reaction is influenced by 9 times. This is for the rate of the reaction. This will be same because coefficients are not given. I believe it will be same for the formation of Y as well. It is increased by 9 times. The rate of the reaction is increased by 9 times. They asked rate itself, so whatever we did is correct. It will influence 9 times. Now let's see the next main topic of integrated rate equations. We have already noted that the concentration dependence of rate is called differential rate equation. The dependence of concentration on the rate, the dependence rate depending on concentration is we call the differential rate equation. And this is not always convenient to determine the instantaneous rate. When we want to find the instantaneous rate, this method is not really convenient as it is measured by determination of slope of the tangent at point T in concentration versus time plot figure 3.1. This makes it difficult to determine the rate law and hence order of the reaction. In order to avoid this difficulty, we need to, for finding in from this law differential rate equation, we need to do many things such as find the tangent, find the slope of the tangent, then find the order, so many steps. For this, to avoid this difficulty, we can integrate the differential equation. Integrate the differential rate equation to give a relation between directly measured experimental data, that is concentration at different times at rate constant. They're saying we can integrate the differential equation to give a relation between directly measured experimental data, concentration at different times and rate constant. Okay, they're saying to integrate the equation. The integrated rate equations are different for reactions of different reaction order. We shall determine these equations for only 0 and first order chemical reaction. Now let's see for 0 order reaction. Let's find the integrated rate law or rate equation for the 0 order reaction. Okay, 0 order reaction means that the rate of the reaction is proportional to 0 power of the concentration. Consider the reaction R to P, rate equals minus dr by dt, K which is equals to K power R power 0. As any quantity raised to power 0 is 1 or unity, rate equals minus dr by dt which is equals to K times 1. So the change in concentration of R equals minus K with respect to dt. Integrating both sides, we will get rate equals minus KT T plus I, where I is the concentration constant of integration. So basically, okay, they integrated both the sides. Dr which is equals to minus k dt, then we know that k is constant, so minus k delta t. So I think this value we will get it as minus k t plus I, where I is the constant of integration, because there is 1 there, I think, right? Yes. Yes, when we are differentiating 1, we will get t, but there will be some constant which we will lose. Because of such a reason, we will add I, or c we can say. I is the integration constant. When we integrate, I think that is the case. When we one with respect to a variable, will we get the same variable? I think this is the case. Where 1 dx, yeah, this is the plus integration constant, c or I we can take. Yes, okay. Here, because this c comes in case, when we differentiate, we can differentiate x plus anything, x plus c, then the answer we will get as 1 itself. Because of such a case, we will take it as x plus c, integration constant. Okay, I understand. That is why we will get the rate equals minus k times t plus the integration constant, where t equals 0, meaning the time is 0, the concentration of the reactant equals R naught, where R naught is the initial concentration of the reactant. Substituting in the equation, minus k times 0 plus I equals the R naught equals I. Substituting the value of I in the equation, basically I think they got the value of I to be R naught plus k minus kt. Can we get the value as in integrated integrated rate expression for 0th order reaction? Yes, we can determine the constant integration C using initial condition, which is exactly basically dA by dt, which is equals to minus k. Integrated form, we will get minus kt plus C is the concentration of the reactant. Usually initial conditions, usually the concentration T equals 0. At T equals 0, at T equals 0 we got I, right? Yes. At T equals 0, plug into the integrated equation, we will get that it is equal to C, which is equal to, now substitute back into the integrated equation, A naught, I didn't get C equals A initial. Okay, I understand right now. Okay, these are basically two equations here. Two equation. The first one we got that for any time t, the concentration of A equals minus kT plus C. We don't know the integral constant or constant of integration C, but let's plug in time equals 0. When time equals 0, the at initial concentration which will be equal to C. Basically they wrote that basically the integrated rate law is, I think it is, what was that, integrated rate law. Okay, for a integrated rate expression for zero order reaction is basically the main differential form of the equation is minus d by r by dt equals, this is a concentration, it's equals to, this is equals to the rate equals k times, for a reaction, this is not k times A, for a reaction R to P. For this reaction it will be k times R power 0. For this is for a zero order reaction, then this will be equal to 1. Now minus dr equals k times dt minus k times dt. Now integrate the equation. Integration of dr is r concentration minus k dt. Now since k is a constant, the rate constant, it will come out, minus also will come out with respect to when we differentiate with respect to 1. We are not taking limits here. Minus k when we differentiate it with respect to 1. This is kt plus integration constant I or C. Now this is the differentiation of the equation we got. Fine. Now let's take case 1. Case 1 where at t equals 0, then r equals minus k times 0 plus I. Okay, fine. Then r equals, this will become r naught, or we can say r initial concentration. Initial concentration equals I. This is, okay, let's take it as, this is as equation 2 and this as equation 1. Now substitute value of equation 2 in equation 1. The equation 1 was the rate, the concentration, the integrated concentration equals kT plus C, where T is time. This can be C or I. We know the value of I equals R initial, so substitute that. R equals K times T plus R initial. R naught is R initial. This is what we got in this equation. anyways, as I was telling, this is the final answer which we got. Yes, basically R equals minus kt plus I. I think I forgot the minus here. Yes, minus will be there. And substituting the value, we will get this R equals minus kt plus R naught. Comparing equation 3.6 with the equation of a straight line y equals mx plus c, where m is the slope, x is the x coordinate and y is the y coordinate. In such a case, equation of a straight line y equals mx plus c, we plot r concentration of r against t, we get straight line with slope minus k, intercept equal to r naught. We get a negative slope because reaction of the concentration of reactant increases as time goes by. I mean decreases as time goes by. Concentration of R reactant, it decreases as time goes by. Further simplifying equation 3.6, we get the rate constant K equals R naught minus R by T. From this equation, we can get K value is R naught minus R initial minus concentration of reactant at time T by the time T. The zero order reactions are relatively uncommon, but they occur under special conditions. Some enzyme catalyzed reactions and reactions which occur on metal surfaces are a few examples of zero order reactions. These are very rare reactions, but we can say they are rare reactions, they are uncommon, and they occur only in special conditions. That is under the action of an enzyme catalyzed reaction or reactions which occur on metal surfaces. This is also a catalyzed reaction, a metal catalyzed reaction. In the enzyme catalyzed reaction, in the metal catalyzed reaction, when the surface is the metal surface, these are the few examples of zero order reaction. The decomposition of gaseous ammonia on a hot aluminum surface is a zero order reaction at high pressure. NH3 gas at 1000 Kelvin with platinum as a catalyst will get nitrogen and hydrogen gas. Rate of this reaction is NH3 whole to the power of 0 equals K. Rate is equal to the rate constant, meaning the rate will remain constant. Condition under same pressure and temperature. Variation in the concentration versus, okay, this is the graph. Variation in the concentration versus time plot for a zero order reaction. Okay, fine. In this reaction, platinum metal acts as a catalyst. At high temperature, the metal surface gets saturated with gas molecules. Okay, platinum is acting as a catalyst. At high temperature, high pressure, the metal surface gets saturated with gas molecules which get accumulated on the metal surface. So a further change in reaction conditions is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of reaction independent of its concentration. Basically, why the reaction of ammonia or zero order reaction of ammonia decomposing is independent of the concentration of ammonia is because at high pressure, on the metal surface, ammonia gets concentrated. Many molecules of ammonia will get saturated at the surface of the metal. So a further change in reaction conditions, like metal surface for example is around 3 meters square, and ammonia is decomposing when it is under high pressure. Ammonia molecules get concentrated here, and they get concentrated as I said before. At high pressure, they get concentrated on the metal surface of the 3 meters square. Okay, then let's say at some concentration of ammonia, this whole metal plate is completely filled to the brim with ammonia molecules. Completely filled. The reaction is occurring, and due to pressure and concentration of ammonia, the surface is completely filled with ammonia molecules. In such a case, if we add more gas of ammonia to the we will increase the concentration of ammonia. In this case, we will increase the concentration of ammonia. NH3 concentration we are going to increase. In such a case as well, since the maximum number of molecules on this metal plate is already filled, even if we increase the number of concentration of ammonia, the number of molecules on the plate will still remain. For example, at some concentration there are 30 molecules of ammonia, maximum 30 molecules of ammonia on the metal plate. 30 molecules. And this is the maximum amount of molecules that can stay on this metal plate. Okay, then we increase the concentration of ammonia. Then as well, the concentration or the amount of molecules on the plate will still remain 30 only. They can't increase because that's the maximum amount. In such a case, no matter how much we increase the concentration of NH3 ammonia, the rate of the reaction doesn't change. That is why these are zero order reactions. Or in case of an enzyme, if a certain amount of enzyme is acting like a limiting reagent or a limiting agent, which is limiting the rate of the reaction. As the enzyme is constant, the amount of enzyme, if it is 3 ml, 5 ml, or whatever the concentration or amount of enzyme is present, that will remain the same, it won't change. In such a case, 5 ml of enzyme reacting with 10 ml of whatever the reactant might be, this 5 ml of enzyme will only react with this 10 ml of reactant. Even if we add 100 ml of reactant, it will still react with this 10 ml of reactant only. So in such a case, it will become zero order reactions. It doesn't depend on the rate, the concentration of the reactant. In this reaction, platinum metal acts as a catalyst. At high pressure, the metal surface gets saturated with gas molecules. So for the change in reaction conditions, is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of the reaction independent of its concentration. A thermal decomposition of HI on gold surface is another example of zero order reaction. Thermal decomposition of hydrogen iodide on a golden surface. Now let's see the integrated rate law for the first order reactions. In this class of reactions, the rate of reaction is proportional to the first power of the concentration of the reactant. For example, from R to P, rate equals minus dr by dt, K times concentration of R. Or dr by R equals minus K dt. Integrating this equation, we get ln of R 1 by R. When we integrate 1 by R, we will get ln R, I believe. This right hand side is the same as a zeroth order reaction. Differentiating minus K dt we will get with respect to 1 integrated with respect to 1, we will get minus Kt plus I. But there is some difference in case of integrating 1 by R with respect to dr. When we differentiate integrate 1 by x, then I don't think there will be a circle there. I'm not too sure. When we integrate 1 by R with respect to dr, we will get ln of R, or when we integrate 1 by x with respect to d of x, we will get ln of x. I think this is the formula. When we integrate 1 by x with respect to d of x, then is the answer ln x. Yeah, it is ln x plus c. Okay, that is why we got this ln r equals minus kt plus I, where I is the integration constant. They seem to not have considered the integration constant here, taking it equal to 0. Again, I is a constant of integration and its value can be determined easily. Taking t equals 0, we can substitute t equals 0 when we get ln of r equals minus kt will become 0, so 0 plus I, so I equals ln of r. So when we take t equals 0, r equals r naught, where r naught is the initial concentration of the reactant. Therefore, reaction 3.8 can be written as ln of r naught is equal to I. Substituting the value in the I equation, we will get ln of r, which is equals to minus kt plus ln of r naught or ri, our initial. Rearranging this equation, ln of r minus ln of r naught can be written as ln of r by ln of r naught, which can be minus kt, or k equals 1 by t ln r naught by r. At time t1, from the equation 3.8, ln r1, which is equals to minus kt plus ln of r naught. At time t2, ln r2, which is equals to minus kt plus ln of r initial, where r1 and r2 are the concentration of the reactants at times t1 and t2 respectively. Subtracting equation 3.12 from 3.11, okay, you will get ln r1 minus ln r2 is equals to minus kt1 minus kt2 ln of r1 by r2, which is equals to k times t2 minus t1. Okay, the first integrated rate equation we got was for initial concentration and final concentration, or the final concentration at time t. This is when we take times t1 and t2 and the final concentration of r1 and r2, when we get ln of r1 by r2, which is equals to k t2 minus t1. And in this case also finding the rate constant 1 by t2 minus t1 times ln of r1 by r2. Equation 3.9 can also be written as 3.9 is this equation, ln r equals minus kt plus ln r naught. This can also be written as ln of r by r naught, which gives minus kt, and taking anti-log of both sides we will get, taking anti-log on both sides we will get r equals r naught e power minus k times t. Comparing equation 3.9 with y equals mx plus c, this equation as well, if we compare it with last straight line equation, y equals mx plus c, but here we take, instead of the direct concentration of the reactant for the first order reaction, we take ln of r versus time graph, versus time graph, where here as well the slope is negative because the concentration of the reactant decreases as the reaction progresses further. We plot in ln r against time, we get straight line with slope equals minus k and intercept equals ln r naught. Let's read first. The first order rate equation 3.10 can also be written, 3.10 is this one, can be written in the form ln we are taking into log 2.303 t log r naught by r, where log r naught by r equals kt by 2.303. If we plot a graph between log r naught by r versus t, the slope is k by 2.303. This we basically compare to the line equation, then we will get, which is basically, if we compare it to the y plus, yes, y equals mx plus c, where c is not considered here. Y equals mx, x is t, m is k by 2.303, which is a slope. Log of r naught by r equals y. Okay, hydrogenation of ethene is an example of first order reaction. Ethene plus hydrogen gives ethane. Rate is k times C2H4. Power 1, this is first order reaction, the power is 1. All natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. All natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. This is a statement to be remembered once more. All natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. Now let's see the graphs. A plot between ln of r and t for first order reaction. As we saw before, it is negative slope. It is similar to the 0th order reaction, and in case of log r naught by r and slope equals k by 2.303, here the slope is not negative. All the base equation for this, I will derive it. The first integrated rate expression for first order reaction I will do it as fast as possible. Minus dr by dt equals k times a power, or for reaction r to p it is r power 1, so differentiation is minus dr by dr, not dr but r, equals minus k dt. Differentiating, integrating, we will get, when we take the minus sign here, it will become positive, so it will be 1 by r times dr, or with respect to dr, and minus k outside dt, which is equal to ln of r equals minus kt plus I, where I equals using substituting t equals 0, we will get I equals ln of r naught. This is in case of substituting t equals 0. Then from this base of an equation we will get ln r equals minus kt plus ln of r naught, r initial, ln of r minus ln of r naught, which is equals to minus kt, which will give us the formula ln equals r by r naught is equals to minus k times t, and k equals minus 1 by t ln of r by r naught. This is our whole ln, and this we can write it as, actually this is not what we are converting right now, so let us not. Basically the whole base of an equation is ln r minus ln r naught equals minus k, or ln r by r naught equals minus k minus kt. This is the whole basic equation. From this we derive all things. Actually, this is not actually the basic one, this is the more basic one. It seems to be a parallelogram. I wanted a square though. Okay. Okay. Fine. Let's continue. And a statement to be remembered is that all natural and artificial radioactive decay of unstable nuclei take place by first order reaction, but just in case, let us confirm it. It is correct. And they gave an example of radium 22688 is having an alpha decay of giving an alpha particle, and radon rate equals k times concentration of radium, decomposition of nitrogen, dinitrogen pentaoxide and dinitrogen oxide are some more examples of first order reactions. The initial concentration of N2O5 in the following first order reaction, N2O5 gives NO2 plus half a mole of oxygen, was 1.24 into 10 power minus 2 at 318 Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 power minus 2 mole per liter. Calculate the rate constant of the reaction. Okay, fine. Log R1 by R2 equals KT2 minus T1 by 2.303. K equals 2.303 by T2 minus T1 log R1 by R2. We will get the value if we do everything. We will get K equals 0.034 per minute. If you want per second, we multiply it by 60. Let us consider a typical first order gas phase reaction. A plus A giving B gas plus C gas. This is a decomposition reaction, which we can take an example of ammonia decomposition. Let Pi be the initial pressure of A and Pt be the total pressure at time t. Integrated rate equation of such a reaction can be derived as total pressure equals Pt equals Pa plus Pb plus Pc. Pa, Pb and Pc are the partial pressures of A, B and C respectively. If x atm be the decrease in pressure of A at time t, okay, and one mole of each of B and C is being formed, the increase in pressure of B and C will also be x atm each. Basically, when in a medium, when at time equals 0, the total pressure will be P, which is equals to pressure of A at time equals 0, P naught A. But as the equation continues to go and the A continues to dissociate, it will lose an x amount of molecules. So P initial minus x ATM is the pressure of A at partial pressure of A at time t. Because it is giving two individual molecules, a partial pressure depends on both of them, and both have a pressure of x ATM, where P is the initial pressure at time equals 0, Pt equals Pi minus x plus x plus x. Then the total pressure is Pi plus x, and the total number of molecules that is lost, or total decrease in pressure, is P total minus P initial, where Pa equals Pi minus x, which is Pi minus Pt minus Pi, which is equals to, where the partial pressure of A will be 2Pi minus Pt. Basically they are saying that for gaseous reactions, A gas gives B gas plus C gas. Now let's assume the pressure initial is equals to the pressure initial of A is equals to the P total at time equals 0. Let's assume at time equals t, the decrease in pressure of A, the partial pressure of A equals P initial of A minus some x ATM of pressure. So since such a case, the partial pressure of B will be at time t, B will be x, and PC will also be x. The total pressure at T equals PA plus PB plus PC. We know that PA equals P initial minus x, PA equals x, PC is also equals x. Now this x cancelled. Now P total at T equals Pi plus x. Fine. Then x we can find out. X equals P total at time t minus P initial. Now substitute this in equation 1. Equation 1 is this one. Equation 1, it will be PA equals Pia minus x. Substitute equation 2 in equation 1. It will be PA equals partial pressure of A at T equals T equals P initial of A minus P total at time T minus Pi. So basically this will become P total equals 2 times PIA minus P total. This is the equation which we got in the textbook as well. Yes, 2 pi minus P total. We know that K equals 2.303 by log of P1 by PA, then 2.303 T by log of P1 by P initial by 2 pi minus 2 PT. The following data were obtained during the first order thermal decomposition of dinitrogen pentaoxide at constant volume. Find, calculate the rate constant. First data is that at time 0 the total pressure is 0.5 atm, okay, and at time 100 second the total pressure is 0.51 atm. There is an increase of 0.012. Okay, calculate the rate constant. K they are asking. K direct formula we have, it is 2.303 by T log of P initial by 2 P initial minus P total. As for how we got this formula, the base first order reaction formula that we did many turns and twists and we got our equation. This is the equation basically, where ln we converted into log and we got that kt by 2.303 equals log of r naught by r, and when we want k we put the we send all things that side, it will become k equals 2.303 by t log of r initial by r, and this is the concentration in case of liquids. This will become pressure initial and pressure final in case of gases. That is how we got the equation, this equation. K equals then basically we will get, let the pressure of N2O5 decrease by 2x times atm. 2 of x of atm as 2 moles of N2O5 decomposed to give 2 moles of N2O4 and 1 mole of oxygen. The pressure of N2O4 increases by 2x atm and that of oxygen increased by x atm. This is because 2 molecules of N2O4 are produced but only 1 mole of or 1 mole of oxygen is produced. In such a case, at time t the total pressure is this. We will get the total pressure x equals P total minus 0.5 and the pressure which will be pressure of N2O5 is 1.5 minus 2 pt, and at time equals 100 P total equals 0.512 atm. Substitute the value in this equation and we will get 0.476 atm is the pressure, partial pressure of dinitrogen pentaoxide. And from doing the calculation by substituting in the formula, taking logs and all, we will get the final value to be 4.9 into 10 power 4 per second. For a first order reaction is the rate constant for the reaction. Now another topic is half-life of a reaction. Okay, now half-life of a reaction. The half-life of a reaction is a time in which the concentration of a reactant is reduced to one half of its initial concentration. It is represented as T half. Basically, half-life of a reaction is the time in which if there is a reaction of A to B, the time it takes for the concentration of A to concentration of A by 2, the time taken here, this time represented as T half, is called the half time. Okay, fine. For a zero order reaction, rate constant is given by equation 3.7, which is R naught minus R by T, where R naught minus R is 1 by 2R and T equals T naught, so T half, so it will be 1 by 2 R naught by T by 1 by T half. This is the time taken. This is what they represented here. Then it will become T half equals R naught by 2K. When we substitute it equals, this is equals to K. This is not a minus sign. This is equals to K. Then shift K that side. T half equals R naught by initial concentration by 2 times of the rate constant. It is clear that T half for a zero order reaction is directly proportional to the initial concentration of the reactants. Higher the initial concentration, higher the time taken, and inversely proportional to the rate constant. Higher the rate constant, lower the time taken. For the first order reaction, K equals to 0.303 by T log R naught of R at T half. When we substitute the value R naught by 2, so basically K equals 3.3303 by T 1 by 2 times log of R initial by R naught by 2, R naught by 2. So this is basically, you can cancel R naught, you will get log of 2.303 by T half. Log of 2 value is 0.3010. I think that is the value. 0.3010, and the T half will be 2.303 into 0.301, which is 0.693 by K. This is for a first order reaction. It can be seen that for a first order reaction, half period is constant. That is, we do not see the concentration terms. So for first order reaction, it doesn't depend on the concentration itself, but it is inversely proportional to the rate constant. Higher the rate constant, the lower the time taken to reach the half concentration, independent of the initial concentration of the reacting species. The half-life for a first order reaction is readily calculated from the rate constant and vice versa. For zero order reaction, T half is directly proportional to R naught. For first order reaction, T half is independent of R naught. A first order reaction is found to have K equals 5.5 into 10 power minus 4 per second. Find the half-life of the reaction. T half equals 0.693 by K. 0.693 by K is 0.693 by 5.5 into 10 power minus 14. So the half time taken is incredibly long, of 1.26 into 10 power 13 seconds. Show that the next question, the next example, in a first order reaction, the time required to complete 99% is 10 times of the half time of the reaction. What? Show that in the first order reaction, the time required for completion of 99.9% is 10 times of the half-life. Okay, let's see. Okay, let's see for the first scenario where when the reaction is 99% completed, we can substitute R naught by R, which will approximately get a value of 10 power 3 log of 10 power 3, which is 3 times 2.303 by K. So 693 is approximately 10 times. It is indeed 10 times when we calculate. Okay, fine. Table 3.4 summarizes the mathematical features of integrated laws of zero and first order reactions. Integrated rate laws of the first order and the zero order reactions are order 0 and 1. Reaction type is a single monomolecular reaction, or at least one reactant reaction. Only one reactant is involved here. And here the differential law is same except for the presence of R here, which is because it depends on the concentration for the first order reaction and doesn't for the zero order reaction. Integrated rate law for zeroth is directly the change in concentration, which is equals to Kt. But here it is completely different, where R0 times e power minus Kt is equal to the final concentration, or Kt equals ln of R0 by R. Here straight line is R versus T, but here we take it as ln R versus time. Half-life is R0 by 2K, here ln 2 by K, or we can say 0.693 by K. Units of K is mole per liter per second, which is same as the rate, and here it is per second. The order of a reaction is sometimes altered by conditions. There are many reactions which obey first order rate law, although they are higher order reactions. Consider the hydrolysis of ethyl acetate, which is a chemical reaction between ethyl acetate and water. In reality, it is a second order reaction, and concentration of both ethyl acetate and water affect the rate of the reaction. But water is taken in large excess for hydrolysis. Therefore, the concentration of water is not altered much during the reaction. Thus, the rate of the reaction is affected by concentration of ethyl acetate only. For example, during hydrolysis, 0.01 mole of acetate with 10 mole of water. Amounts of the reactants and products at the beginning T equals 0 and the completion T of the reaction as given as under, where this is ethyl acetate plus water will give at time equals 0, there it is 0.01 mole, and water it is 10 mole. And when the reaction is completed in presence of an acidic medium, it will be acetic acid or ethanoic acid plus C2H5OH ethanol. The concentration is 0.01 mole and 0.01 mole here as well. When we see the change in concentrations here, water reduced extremely minute, where 9.99 mole. It is almost same as before the reaction. So basically what they are saying is, all pages are over. equations are, equation has been taken here, fine. Basically, when we take for a second order reaction, rate is dependent on A as well as B, or it is 1 and 1. This is a second order reaction. But in a special case, let's assume for a reaction we took A to be 0.01 mole and B to be 10 mole or 100 mole or 1000 mole, or let's take infinity. It's not really infinity, but the distance we can consider it as infinity. Not distance, but the amount comparatively we can say it is close to like very very high. It's not really infinity. In such a case, even though this reaction is proceeding forward and the product C or D is formed, A plus B gives C and D, even though it is formed, the concentration of A reduced to 0 after reaction, but B, it is still the same, almost the same. And when we consider it as infinity, no matter how much the concentration of B is used in the reaction, it will still be the same. In such a case, for example, not infinity or 100 mole as well, it will still be 99.99 mole. In such a case, from time 0 to time initial time t or final time t final, there is no change in concentration of B, almost no change in concentration of B. In such a case, why would we do not consider the concentration where we take in excess? This we do not consider, and we only consider the limiting, we can say the limiting reactant basically. This is what which is getting used up, and this is what depends on the mainly the reaction. That is what they said here. The concentration of water does not get altered much during the course of the reaction. So the reaction behaves as a first order reaction. Such reactions are called pseudo first order reaction. Inversion of cane sugar is another pseudo first order reaction where the amount of H2O is constant. I mean, yeah, it is constant, it's almost constant. Glucose and fructose is formed. Rate depends only on the concentration of the cane sugar or sucrose. In text question, a first order reaction has a rate constant 1.15 into 10 power minus 3 per second. How long will 5 gram of this reaction take to reduce to 3 gram? Okay, this is basically using one of the equations from the first order reaction. From here, some of the equations we can use. Well, they gave in grams, so we can convert it into per liter or molar. Then we should substitute, I believe. This is okay, fine. When we should convert it into concentrations, then take these equation where K equals this and log of R naught by R. Wait, no, I think that is not the case here. They are asking, yes, they are asking the time, so yeah, it is, we should use that formula only, yes. This is similar to half reaction, so we should use the same formula and we will get the answer. We should substitute in the formula, everything is given except time, everything if we substitute. When we can take it as, since they didn't give the concentration, we can take the concentration to be around 1 liter or 100 ml or whatever we want. And The next question, time required to decompose thionyl chloride to half of its initial amount is 60 minutes. If the decomposition is a first order reaction, calculate the rate constant of the reaction. Basically they gave value of t half. They said that n equals 1, and for n equals 1 we know that t half equals 0.693 by k. Now t half they gave us 60 equals 0.693 by k, so k equals 0.693 by 60. This, if we calculate, we will get the value of k in terms of minutes, but if we want to convert it into seconds, then 0.693 by 60 times 60, it will be 0.693 by 3600. Wait. Yes, that is correct. 3600. Now let's go to the next topic, which is the next main topic, temperature dependence of the reaction, of the rate of the reaction. Temperature dependence of the rate of a reaction. Most of the chemical reactions are accelerated by increase in temperature. For example, in decomposition of dinitrogen pentaoxide, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degrees, 5 hours at 25 degrees, and 10 days at 0 degrees. At 50 degrees temperature, it will be happen as fast as 12 minutes, and at 25 degrees or room temperature or little less than room temperature, if we take, it will take 5 hours or so. But if we take it at 0 hours, a drastic increase, it will take 10 days for the half reaction to happen. You also know that in a mixture of potassium permanganate KMnO4 and oxalic acid H2C2O4, potassium permanganate gets decolorized faster at higher temperature than at lower temperature. Basically, they are indicating with examples that temperature is directly proportional to the rate of the reaction. Generally, it has been found that for a chemical reaction with a rise in temperature by 10 degrees, the rate constant is nearly doubled. It has been found, this is an important value or statement we can say. It is found that for a chemical reaction with a rise in temperature of 10 degree, the rate constant is nearly doubled. If K initial at T initial, then T initial plus 10 equals 2 times of K initial. This is what they are saying. Okay, fine. Nearly doubled. Okay, it will get doubled. Okay, let's see. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. Let's see the 3.18 equation. No, it is not here. 3.18 is K equals A times E power minus EA by RT. The temperature dependence of a rate of a chemical reaction can be accurately explained by Arrhenius equation. It was first proposed by Dutch chemist J.H. van 't Hoff, but Swedish chemist Arrhenius provided its physical justification and interpretation. It was first proposed by van 't Hoff, but Swedish chemist Arrhenius provided its physical justification and interpretation. The Arrhenius equation is the rate constant equals A times E power minus EA by RT, where A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. It is a constant specific to a particular reaction. It depends on the reaction actually. It's not a complete constant. It depends on the particular reaction. That is basically why they call it the frequency factor. R is a gas constant and EA is activation energy measured in joules per mole. It can be measured clearly using the following simple reaction. This is the formation of HI through the intermediate, where HH will react bond formation here, here, and bond breaking here and here. It will give HI and HI. H2 gas reacting with I2 gas gives HI. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. This intermediate, it exists for a very short time and then breaks up to form two molecules of hydrogen iodide. Fine. The energy required to form this intermediate called activated complex. Basically, they are calling this intermediate as the activated complex. Fine, so many names, but fine. It is denoted by C, I believe. Here it is given. Is known as activation energy EA. Energy required to form this intermediate or the activation complex is known as activation energy, denoted by E subscript A. And figure 3.7, obtained by plotting potential energy. Let's read first. Obtained by potential energy versus reaction coordinate. Reaction coordinate represents the profile of energy change when reactants change into products. Reaction coordinates means the energy change when the change in energy when the reactants are converted into products. This energy change is what we call the coordination energy. Wait. Obtained by plotting. The reaction coordinate. Yeah. Potential energy, reaction coordinate. Okay, fine. H2 plus I2. Activation energy. This is the activated complex. Due to this high energy, it is reactive and it loses energy. And finally, the product 2HI with a reaction coordinate of delta H is formed. Some energy, but I think this is reaction coordinate is basically the step or indicating the specific place of the reaction, or not the place but indicating the going through reaction. Some energy is released when complex decomposes to form products. So the final enthalpy of the reaction depends on the nature of the reactants and products. All the molecules in the reacting species do not have the same kinetic energy. Yes, since it is difficult to predict the behavior of any one molecule with precision, Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. Basically, in a molecules, in a gas atom, or not atom, in a gas mixture if we take, or just a gas bottle if we take, we cannot individually predict the single molecule's kinetic energy, potential energy, the direction, the movement. We cannot, it's very hard to predict. So that is why Ludwig Boltzmann and James Clerk Maxwell, they use statistics to predict the behavior. They use statistics to predict the behavior of a large number of molecules. According to them, which is Boltzmann and Maxwell, the distribution of kinetic energy may be described by plotting the fraction of molecules Ne by Nt with a given kinetic energy E versus kinetic energy. Here Ne is the number of molecules with energy E and Nt is the total number of molecules. Ne is the number of molecules with energy E. Basically, they defined, or basically they gave a single molecule some amount of energy, some amount of kinetic energy, and Ne is the total number of molecules having that energy. But shouldn't the total number of okay, fine, the total of, I think not all the molecules possess the same amount of energy, each individual molecule, so that is why they don't cancel out. If all the molecules in that mixture or in that bottle have the same amount of energy, then there is no need to plot this graph. So he basically defined a specific amount of energy for some Ne amount of molecules, and this Ne is the number of molecules having that amount of energy, that specific amount of energy, and N is the total number of molecules present in that bottle. And they plotted according to them the distribution of kinetic energy, and we described the plotting the fraction of molecules with a given kinetic energy, fraction of molecules. Let's see the graph first. Fraction of molecules, kinetic energy. Kinetic energy increases as the fraction Ne by Nt increases. Ne by Nt, how will this increase? It will increase when Ne increases or Nt decreases. Ne increases when the number of molecules having the specific amount of energy increases. Our predicted energy, that energy molecules increases, then the total number, this value fraction will also increase. So when we plot this graph, okay, this I think yes, between kinetic energy, okay, yes, and basically the prescribed specific energy, they did not take it to be constant, the kinetic energy. That is why they plotted like this. As we move through this graph, the kinetic energy is changing, the specific kinetic energy is changing. So this Ne value is continuously changing as we move through this graph. The total number of molecules will not change, but this fraction value will continue to change as the number of molecules having 0 or 1 joule per mole energy, there might be some 20 molecules, and it will be somewhere here, and the molecules having 30 joules of energy, which may be 300, which may be here. So when this fraction reached the highest value, that is there, according to them, this is the most probable kinetic energy. This is the most probable kinetic energy because most of the molecules have this energy that they are saying. Distribution of curve showing energies among the gaseous molecules. The peak of the curve corresponds to the most probable kinetic energy, that is kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than the value. I will discuss this, if I remember, once more at the end when I have time. Distribution of curve showing temperature dependence on the rate of reaction. This is kinetic energy. This is the fraction of molecules. Wait, this is the same thing again. Let's read the statement again. The peak of curve corresponds to the most probable kinetic energy. That is kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with increasing energies higher or lower than this value. When the temperature is raised, when we increase the temperature, the maximum of the curve moves to higher energy value. Let's say we are increasing the temperature, the kinetic energy also will increase. Then this will be, this graph will also move like this, and the new most probable kinetic energy will be increased. These molecules will have higher energy when compared to T1. The molecules in T2, the most probable energy in T2 is higher than the most probable kinetic energy in the T1. This area shows the fraction of molecules reacting at T. This is at T. When we increase the temperature by T plus 10, and we see that the most probable is around here, which is here, and this is at T, it is here. The kinetic energy of the most probable has increased, and energy of activation seems to be also higher for this graph. Energy of activation, for higher the temperature, higher the energy of activation required. By seeing this graph, I think that is the case. Fraction of addition of molecule, which, okay, as we increase the temperature, as we see, this area shows the number of molecules reacting to give a product, this area. In the first case, when there is only one graph, this is the area of the molecule, this is the amount of molecules reacting. But as we increase the temperature, if this might be 10, when we increase the area of the, temperature, it's not like this. In this case, when we see the number of molecules in this area, the area has increased. The number of molecules has become 20. It is not actual values, but the number of molecules reacting to form the product has increased. We cannot say in a reaction, we cannot say all the reactions will react to give a product. And this is the energy of activation has also slightly increased here, because more number of molecules, more number of energy required, so more amount of energy of activation required. Energy of activation is required for providing the complex formation. The activation complex or the intermediate formation. For this activated complex to form, this intermediate to form, we need activation energy. That activation energy also, because more number of molecules are participating, the energy for activation also increased. The maximum of the curves moves to the higher energy value, and the curve broadens out, that is, spreads to the right, such that there is a greater proportion of molecules with much higher energies. The area under the curve must be constant, since total probability must be 1 at all times. The area under the curve must be constant. Okay. As the number of molecules will never increase, this will, as the curve was around like this, area is 20 meter square. This is indicating the total number of molecules inside the reaction. And when we increase the temperature, there is a new curve found. This curve, under this curve, the area will also be 20 meters square. That is because the number of molecules in the inside the area or inside a bottle will always be the same number of molecules. Mass can neither be created nor be destroyed. We can mark the position EA on Maxwell-Boltzmann distribution curve. Anyways, increasing temperature of substance increases the fraction of molecules which collide with energies greater than EA. It is clear from the diagram that curve A at T plus 10, the area showing the fraction of molecules energy equal to or greater than the activation energy gets doubled, leading to the doubling of the rate of the reaction. In Arrhenius equation, the factor E minus EA by RT corresponds to the fraction of molecules that have kinetic energy greater than EA. This is basically equal to K, right? Yes, K. Fraction of molecules that have kinetic energy greater than EA, taking natural logarithm of both sides of the equation. Ln K equals minus EA RT plus ln A. The plot in ln K versus 1 by T gives straight line according to the equation 3.19 shown in the figure 3.10. Here a plot between ln K and 1 by T gives a straight downward curve. The slope is minus EA by R and intercept is ln A. The y-intercept is ln A. It's going from ln A to 0 in a straight curve, and not a curve but a straight line. Thus, it has been found from Arrhenius equation that increasing the temperature or decreasing the activation energy result in an decreasing the activation energy. If we are decreasing the activation energy also, the number of molecules inside the activation energy region will be more than the before decreasing the energy of activation. Because of such a reason, either increasing the total temperature by pushing the molecules, more amount of molecules to have the same to step into the range of activation energy, or decreasing the activation energy to push the activation energy to a range of more molecules having the amount of energy. This will increase the rate of the reaction. And an exponential increase in the rate constant. In figure 3.10, slope minus EA by R and intercept ln A, so you can calculate EA and A using these values. At temperature T1, 3.19 is ln K1 minus EA by RT1 plus ln A, basically substituting in the equation. At temperature T2, just again same thing. Since Arrhenius factor or the frequency factor is constant for a given reaction, K1 and K2 are the values of the rate constant at temperatures T1 and T2 respectively. Values of rate constants at temperatures T1 and T2. K1 and K2 are the values of rate constant at temperatures T1 and T2. Fine. Subtracting 3.20 from 3.21, we obtain, basically we are subtracting this from this. No, wait. We are subtracting this one from this equation. We obtain K2 minus ln K2 minus ln K1 is equal to E by RT1 minus EA by RT2. Here the constant terms are activation energy and the gas constant, to take them common this side, and formula ln K2 minus ln K1 equals ln K2 by K1. Then we will get, if we are substituting log, so we will get EA by 2.303 R times 1 minus T1 by 1 minus. This is basically for when we change the reaction, what will be the change in rate constant, or there's no change in activation energy. Basically equation for change in temperature. What will be the change in rate constant? If they ask a question, what will the change in rate constant if there is a change in temperature, or when they give that there are two rate constants at two different temperatures, find the temperature, what is the temperature or what is the activation energy also we can find using this equation, or just this equation, this formula. The rate constant at 500 Kelvin and 700 Kelvin are 0.02 second and 0.07 second. Calculate the values of EA and A. Basically, as I said before, they're asking EA and activation energy and Arrhenius constant. Basically, when we do all the math here, you will get activation energy, which is equals to 18,230.8 joule. And substituting in the Arrhenius equation, K equals A times E minus EA by RT. We can substitute any one of the T values. Then we can substitute here 500. In such a case, we will substitute okay. By doing this maths, we will get the final Arrhenius constant value to be 1.61. The first order rate constant for decomposition of ethyl iodide reaction at 600 Kelvin is 1.60 into 10 power minus 5 per second. Its energy of activation is 209 kilojoule per mole. Calculate the rate constant of the reaction at 700 Kelvin. Basically, as I said before, the same thing they are going to ask. By doing all the math, substituting in the equation, we will get K2 equals 6.36 into 10 power minus 3 per second. Now, one of the next main topics is the effect of a catalyst. A catalyst is a substance which increases the rate of reaction without itself undergoing any permanent chemical change. For example, magnesium dioxide catalyzes following reaction, so it increases its rate considerably. Potassium chlorate in presence of magnesium dioxide will give potassium chloride and oxygen. The word catalyst should not be used when the added substance reduces the rate of the reaction. Okay, it does not control the rate of the reaction or reduce the rate of the reaction. It increases the rate of the reaction. Then only we can call it as a catalyst. If this substance which we added reduce the rate of the reaction, then we call this substance as an inhibitor, not a catalyst. The action of a catalyst can be explained by intermediate complex theory, whatever that is. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. Okay, basically they are saying how this catalyst participates in the reaction. For example, catalyst participates in a chemical reaction. Basically they are saying, when let's assume there is metal surface, example of decomposition of NH3. There is a metal surface of, I think, platinum. No, decomposition of ammonia is let's see, they called it the intermediate complex theory. Fine. What is the catalyst for decomposition of ammonia? Yeah, it's platinum. Platinum, this is the platinum surface. This is the platinum surface, platinum, and here ammonia gets concentrated here. That is why this is a zero order reaction, because when the maximum amount of substance or molecules that can get concentrated on the metal surface is reached, no matter how you change the concentration, if you increase the main rate of the reaction will not change. This is the accumulation of NH3 here. Basically what this intermediate complex theory means is, this platinum is actually making, if this is a platinum surface, NH3 bonding is this platinum, which has extra electrons, will form transient or intermediate, which is not a long, a temporary bond formation. This platinum, having many amount of free electrons, will form bonds with these NH3 molecules. This bond formation will reduce the dissociation enthalpy of the NH bond. This intermediate formation, this is not a permanent. Platinum is not having a permanent chemical change. It is just utilizing its free electrons to form bonds. This bond formation will reduce or weaken this NH bond. Higher bond length meaning, or higher bond length, or this bond meaning less dissociation enthalpy, more dissociation enthalpy. This we can break easily. It will take more energy to break the bond. In such a case, the activation energy required for this reaction, EA, is reduced when in presence of catalyst. Because it is reducing the total bond dissociation enthalpy, which will reduce the complex action complex formation. Action complex is needed to be formed with the help of activation energy. In such a case only reaction will occur. But here, when it is reducing the bond dissociation enthalpy, the formation of the this action complex, the energy required to form the action complex is also reduced. That is why we say activation energy is reduced. That is how catalysts work. That is also, I believe, the intermediate complex theory. Forming intermediates to reduce the bond enthalpy. Let's read once more. The catalyst should not be used when added substance reduces the rate of the reaction. The substance is then called, when it is reducing the rate of the reaction, it is called an inhibitor. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with reactant, resulting in intermediate complex. This has a transitory existence, meaning it only exists for a brief instant, or just saying that it's temporary or it's not permanent, and decomposes to yield products and the catalyst. This bonds, whatever formed here, will be broken later, and the normal decomposition of ammonia takes place, which is NH3 to NH3 gives N2 plus 3H2. This reaction will happen. It is believed that the catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactant and product, and hence thereby lowering the potential energy barrier as shown in figure 3.11. Basically, this catalyst is providing, normally we saw some reaction of H2 plus I2. Basically this is H and H will collide here like this, a transient state of this bond breaking, and this bond breaking is formed. and these bonds are broken and we'll get two HI molecules. This is one of the mechanism for the reaction to occur. But in this, when there is a catalyst present, it is providing a different reaction with much lower activation energy. It is providing a shortcut path which needs less activation energy. That is what is happening. That is what they said here. And here we see the graph, which is a potential energy graph, the total energy or potential energy. This is the reaction coordinate. Basically it can't define reaction coordinates, just the coordinates of the reaction, middle of the reaction basically, or when the reaction is going through. This is the reactant which is at the ground state. It is getting potential energy, and this is the potential energy it is gaining when without catalyst it is at this state. This is the potential energy, this is the activation energy, whatever this is the activation energy they gave here. This is the activation energy without catalyst. Now when with a catalyst, the activation energy is reduced, and both are reaching the same product. Basically we are reducing the cost, reducing the energy, basically making it more energy efficient. All this energy will not be stored in the product, it will again be released again. But the activation for the formation of the action complex, we need this energy. It is clear from Arrhenius equation 3.18, basically K equals A e power minus A or something like that. Yes. Now here A equals e power minus EA by RT. It is clear from our Arrhenius equation that lower the value of activation energy, faster will be the rate of the reaction. Great. Why we are studying activation energy? Because if the lower the activation energy, the more the molecules, according to the Arrhenius and according to Maxwell and Boltzmann, they defined something here. I'll again do it in the last. Effect of a catalyst on activation energy. A small amount of catalyst can catalyze a large amount of reactants. Okay, basically a small amount of catalyst can catalyze a large amount of reactants. A catalyst does not alter Gibbs energy. It does not alter the Gibbs energy delta G of a reaction. It catalyzes a spontaneous. The catalyst, what is doing, it is only providing a different path. It is not messing with the energy. It is not messing with anything. It's just giving a different route. It catalyzes a spontaneous reaction but does not catalyze non-spontaneous reactions. It can only catalyze spontaneous reactions, instant reactions, or a single step reactions. Basically it can catalyze a single step reactions, but it cannot catalyze a non-spontaneous reaction. It is also found that a catalyst does not change the equilibrium constant of a reaction, rather also found that a catalyst does not change the equilibrium constant of a reaction, it does not change the equilibrium constant, rather it helps in attaining equilibrium faster. This point we read it yesterday in solutions chapter as well. Catalyst does not alter the equilibrium constant, it just makes the reaction to occur to attain equilibrium faster. That is, it catalyzes the forward as well as the backward reactions to the same extent, so equilibrium state remains same but is reached earlier. This is the point to be remembered. The equilibrium constant I will be back. Okay, now let's start with collision theory of chemical reactions. Collision theory of chemical reactions. Okay. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Trotz and William Lewis in 1916 and 18, provides a greater insights into the energetic and mechanistic aspects of the reactions. Fine. It is based on the kinetic theory of gases. According to this theory, the reactant molecules are assumed to be hard spheres and reaction is postulated to occur when molecules collide with each other. The number of collisions, basically they are saying, although Arrhenius equation we can calculate constant, rate constant and all, they are saying collision theory is better, which was created by William Lewis and Max Trotz in 1916 to 18. This provides greater insight like how the mechanistic aspects of the reactions work. Basically here it is based on the kinetic theory of gases. They assume the molecules to be hard spheres, individual spheres, and reaction occurs when these two spheres collide. They are two hard spheres. When they collide, here, when they collide, that is when the reaction is occurring. That is what they say. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency Z. The number of collisions per unit volume of the reaction mixture per second per unit, okay, per second, number of collisions per volume of the mixture per second is known as collision frequency. Z, atomic number, but collision frequency. It's not related to atomic number. Another factor which affects the rate of chemical reactions is activation energy. As we have already studied, for a biomolecular elementary reaction, A plus B gives products. Rate of reaction can be expressed as rate equals ZAB e power minus E8 by RT. Wait. Basically they are saying this is the rate of the action where Arrhenius equation is giving the constant K, is giving the value of K. Wait, no. K equals A times E power minus EA by RT. So A is missing here, but they are saying in place of A they substituted collision frequency, and collision frequency they are directly giving the rate here, where ZAB represents the collision frequency of reactants A and B, and E power minus EA by RT represents the fraction of molecules with energies equal to or greater than EA. This part represents the fraction of molecules with energies equal to or greater than activation energy. Comparing 3.23 with Arrhenius equation, we can say that A is related to collision frequency. This equation and this equation, if we compare, we can say A is related to collision frequency. Equation 3.23 predicts the value of rate constant fairly accurately for reactions that involve atomic species or simple molecules, but for complex molecules significant deviations are observed. This is possible. This equation will give us rate constant for simple reactions, but for complex molecules and significant deviations are observed. For complex reactions or complex molecules, significant deviations are observed. The reason could be that all collisions do not lead to formation of products. Why is showing deviation? Because like Not all collisions will lead to a formation of a product. That is kind of obvious, but they gave here. The collisions in which molecules collide with sufficient kinetic energy, called threshold energy, and proper orientation so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products, is called as effective collisions. Basically, the sufficient kinetic energy required for the molecules, this is called the threshold energy, and proper orientation of the molecules. So this should be so that this should facilitate in breaking of the bonds between reacting species and the formation of new bonds. You should break the bonds and formation of new bonds. The two molecules, it's better to use word. Two molecules having a kinetic energy, orientation, and this kinetic energy, the energy, the energy, and sufficient for bond formation, for bond breakage first, for bond breaking and forming, is called threshold energy. This kinetic energy should reach the threshold energy. When these two molecules collide, this is the collision. This is the collision. This collision should have enough energy to facilitate bond breaking and bond formation. Then only a reactant or a final product is formed. The final product is formed. And not always all these collisions, then this should have a specific orientation as well. If this doesn't have a specific orientation and its kinetic energy doesn't reach or is not sufficient to reach the threshold energy, then there is no product formation. If total energy not equal to threshold energy, or if in wrong orientation. If in wrong orientation or when threshold energy isn't reached, then there is no product formation. And when this product is formed, when all the orientation is reached, the energy threshold energy is reached, then when the new bonds are formed and product is formed, that collision is what we call effective collision. For example, formation of bromomethane plus OH minus will give methanol plus bromide ion. Methanol from bromoethane depends upon the orientation of the reactant molecules as shown in figure 3.12. Diagram showing the molecules having proper and improper orientation. This is basically bromomethane, OH minus. Improper orientation is when bromine and OH minus are in the same direction. Here no product is formed because minus minus repulsion. But the proper orientation is when OH minus basically OH minus should be meeting C plus. C is having a partial positive charge, Br is having a partial negative charge, and there are 3 CH3, or like this. OH minus should meet C plus in this orientation. Then only bond making will happen. Like this is a transient stage. Then methanol is formed, leaving the breaking of the bond of the bromide, forming the bromide ion. The proper orientation, reactant molecules lead to bond formation, whereas improper orientation make them simply bounce back and no products are formed. To account for effective collisions, another factor P called probability of steric factor introduced. We need to know, we can define threshold energy based on energy needs, activation energy needs, and basically it will come under that category. That threshold energy is reached when all the molecules have a certain amount of collision, certain amount of energy. It will come under the activation energy and such. But the second factor, that is orientation, to define this orientation, we bring in a new quantity or another factor, that is probability or steric factor, denoted by P. What is the probability of orientation, correct orientation? It takes into account the fact that in collision molecules must be properly oriented, that is rate equals the probability times, normally the rate was ZAB e power minus EA by RT, but introducing the P factor, if P factor I think can only be between P factor can be between 0 and 1, 0, 1. It cannot be greater than 1, I think. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. Collision theory, activation energy and proper orientation of molecules together determine the criteria for effective collision and hence the rate for a chemical reaction. Okay, they're saying it depends both on the energy and proper orientation. Basically, same thing they repeated here again. Collision theory also has certain drawbacks as it considers atoms, molecules to be hard spheres and ignores their structural aspect. Not all molecules are hard spheres, so we cannot consider or approximate that. You will study details about this theory and more other theories in your higher classes, maybe degree. Threshold energy is equal to activation energy plus energy possessed by reacting species. Okay, basically adding activation energy to the already possessed energy. With this, we have completed the chapter, but I will indeed read the summary. Chemical kinetics is the study of chemical reactions with respect to reaction rates, effect of various variables, rearrangement of atoms, and formation of intermediates. The rate of a reaction is concerned with decrease in concentration of reactants or increase in concentration of products per unit time. It depends on time, reactant concentration. It can be expressed as instantaneous rate at a particular instant of time and average rate over a large interval of time. A number of factors such as temperature, concentration of reactant, catalyst affect the rate of the reaction. Mathematical representation of rate of a reaction is given by rate law. It has determined experimentally and cannot be predicted. Order of a reaction with respect to a reactant is the power of its concentration, which appears in the rate law equation. The order of a reaction is the sum of all the powers of the concentration of the terms for different reactants. Rate constant is the proportionality factor in the rate law. Rate law and order of a reaction can be determined from the law or its integrated equation or rate equation. Molecularity is defined only for an elementary reaction. Its values are limited for 1 to 3, whereas order can be 0, 1, 2, 3, or even a fraction. Molecularity and order of a reaction, elementary reaction, are same. Temperature dependence of rate constant is defined by Arrhenius equation. EA corresponds to the activation energy and is given by the energy difference between activated complex and the reactant complex. It's actually the activated complex, not the action complex. And A, Arrhenius factor or pre-exponential factor, corresponds to the collision frequency. Collision frequency is the number of collisions per volume per second. The equation clearly shows that increase of temperature or lowering of activation energy will lead to an increase in the rate of the reaction and presence of the catalyst that lowers the activation energy by providing an alternate path for the reaction. According to collision theory, another factor P, called steric factor, which refers to orientation of molecules which collide, is important and contributes to effective collisions, thus modifying the Arrhenius equation to K equals P ZAB e power minus EA by RT. With this, I have completed chemical kinetics, revision 1 via NCERT is completed. I will see you in the next video.